Okay, so this is the first problem from the 2022 FRQ. So you guys will get to see basically what the FRQs look like. This first problem is very all-encompassing. It's like a bunch of different topics put together. So let's start with part A. So it's telling you that a student is reacting 0.3 grams of this and with a strong base, and then you produce salicylic acid. Okay, so this is a pretty easy question. It's just basic stoichiometry, and I know we haven't done stoic, like straight up stoic, in a while. So I'm actually going to give you guys about 2 minutes. Try this out. You don't need to find any of the molar masses. They're given for you already. So see if you guys can solve out this problem. Okay, take about 2 minutes. It's just basic stoic. Okay, so for this one, your starting value is 0.3 grams of, I'm just going to write MS to abbreviate it. And just regular stoic, so you're going to use the molar mass of this compound right here. And so you'll put 152.15. Oh, excuse me. Oh,
Bless you.
Dang, did not even see that coming. Okay, under 1 mole. And this is all talking about MS. And then it tells you that it's a stoichiometric amount. And so you can kind of infer from that it's a 1-to-1 ratio. So 1 mole of MS is going to produce 1 mole of salicylic acid. And then it gives you the molar mass of salicylic acid, which is 138.12 grams. Okay. And that's going to give you a final answer of about 0.27 grams of salicylic acid. Okay. So that's about as basic as possible for stoic. Okay. That's about as pH 14 as it can get. Okay. Yeah, that's what my wife says. Exactly what she says. Okay. Any questions? Easy peasy? Hopefully it's not too bad. Okay, so congrats, guys. If you guys got that, you got 1 point on last year's FRQ already. Every point counts to a 5. Okay, let's move on. All right, so for this next part, the question is down here in part B, and part here up here kind of gives us the, I guess, what's going on. So let me read the scenario. I'll paraphrase it for you guys, but basically, the student's doing an experiment to purify the salicylic acid after running the reaction. And then basically what the student does is creates the crystals, filters them, rinses the crystals with distilled water, and dries them. And then down here, we got some physical properties of salicylic acid. So you got the melting point, solubility, specific heat of fusion, etc. Okay. Basically, the student does the experiment and only makes 87% yield. So obviously, we can never make 100% yield, but the student makes 87% yield. And then the suggestion that the student makes is that some of the salicylic acid dissolved in the distilled water when it was being rinsed. Basically, based on this information, is that claim consistent? Okay, so I'm going to give you guys about a minute to think about this and just talk it over with the person next to you. I'm going to go over in a second, but you try to use this information right here to determine whether or not the student's suggestion is plausible. It doesn't have to be 100% the reason why, but if it's consistent or not. Okay, so I'll just give you guys the answer straight away, but the answer is yes, it does make sense. Okay, and the reason why, we always have to refer back to the information that we're given. So if we take a look at this, let's just talk about which one of these properties we should be thinking about when we're looking at this scenario. Okay, are we talking about anything melting? No. Are we talking about solubility in water? Yes. So this is what you're going to be looking at. And these don't really matter for this problem. So you're going to be looking at the solubility. So if you take a look at salicylic acid in water, if the solubility is 2.2 grams per liter, it means it does dissolve in water, right? And so that's the reason why the answer is yes. The student's claim is consistent with the physical properties because, and the answer is as simple as salicylic acid dissolves in water. Yeah, that's it. And then you can refer to this right here. Yeah.
Do they ever get points or just like oneers?
Oneers. So each question is worth a different amount of points. So I'll actually post the answer key after you guys turn this in, just so you guys can, and after I'll give it back, obviously. But you guys can see how they'll be graded.
You can't say yes, like yes.
Yeah, you'll have to justify. You have to, if it whatever it asks you, you have to give that. Okay, so I'm actually a little bit more lenient with my grading because I would give you like half a point for just writing yes. But I think for this one, you'll have to write yes and justify for the point. Yeah.
So for FRQs, let's say you put part B by part B by the
Yeah, they're different points.
Would people grading it give you a 0 out of that if you did get 1 point?
Huh? You get partial points. So every part is worth a different amount of points, and you get points for the ones you got right. Okay, let's move on to part C. So part C, make sure you guys have this up on your screen or on your Chromebook because we'll need this table. But for part C, we're looking at the physical properties on the table again. And basically you want to calculate the amount of heat that you need to use in order to increase the temperature of dry salicylic acid from 25 degrees to the melting point and to melt the crystals completely. Now, if you guys remember back from the thermochem unit, we had that chart, right? Where we have the enthalpy. Yeah. You love this chart? Yeah, so yeah, this is where you start, right, as a solid, right? And then once you get to the melting point, all the melting stops. And then when everything is melted, temperature can rise again. Then it needs to vaporize and then go all the way up to gas. Okay, so since we're talking about dry salicylic acid, which phase of matter are we starting in? Solid. We're starting in solid. Now it tells us the temperature that we start at. The temperature that we start is 25 degrees Celsius. Oops. Yeah, my fault. So this is the energy and this is the temperature, sorry. So 25 degrees Celsius. We go up to the melting point, which is 159. And then we want to melt the crystals completely. So there's two calculations that you need to do. The first calculation is to heat up the salicylic acid to the melting point. The second calculation is how much energy does it take to actually melt the salicylic acid completely. Okay. So again, it's a two-part calculation. First is the raising the temperature. The second is the melting. So I'm going to give you guys about 3 or 4 minutes to try this out. You guys will probably need the AP equation sheet. I got extra copies up here if you need them. But try to get used to just doing the problems with the equation sheet and the info given, because that's what you'll have to do on the test. Obviously, you'll need a periodic table, so you can use that. But try to get into practice using those two things. Okay, so I'll give you a couple minutes to do that. Okay, so for the first step, we're talking about the heat of, heating. Right, just heating the sample. So we'll on the AP handout, you should have M specific heat delta T. So this is the equation sheet that you should be using. So you'll start with 0.105 grams. Okay, the specific heat, if you take a look, is 1.17 joules per gram degree Celsius. And then the delta T will be 159 minus 25. Okay, and since it's Celsius, and it's change, you guys don't need to convert it to the absolute temperature because the change is going to be the same. Okay, but you solve that out, you should get 16.46 joules. Okay, for the heating. Okay, for the second one, this is a lot easier. It's just going to be the mass, and it's just going to be multiplied by the heat of fusion. Okay, so it'll be fusion. Okay. Oh, sorry, but if you take a look at the table, the heat of fusion is given in moles, right? So you're gonna have to convert the mass into moles. So we're going to do 0.105 grams, and then you'll have to use the molar mass, 138.17 grams. Okay, so this is going to be your mass, and then you're gonna multiply that by the heat of fusion, which is 27.1 kilojoules per mole. Okay, so if you did it in a separate equation, that's totally fine too. But for your answer for this one, you should get 0.0206 kilojoules. Okay, if you got it in joules, that's fine as well. Okay, 20.6 joules. Yeah. Yeah, moles is fine. Yeah, if you can just punch in your calculator and get moles, that's totally fine. Okay. Yes. You did in moles?
Yeah.
That wouldn't work because if you look at the table, the specific heat, the units of measurement is grams or joules per grams degrees Celsius. So you have to have it in grams. Yeah, or it won't work out. Yeah. So yeah, be really careful while you're looking at the units of measurement. All right, so you put them together. Yeah.
Oh, do you need to add them?
Yeah, you need to add
Okay.
them. Yeah. So yeah, third step, which is the last step, you put them together. Just add them together. 37.06 joules. Okay. If you put in kilojoules, that's totally fine as well. 0.037 kilojoules. Yeah, if you want to. If you want to annoy them more, feel free. Whatever you like. Millijoules, picojoules, nanojoules, megajoule, terajoules. Okay. Make sense? So yeah, this is like all blast from the past stuff, right? It's a long time ago. Okay. Let's move on to the next part. So part D. All right, so you got the structures and the melting points for the two compounds we're talking about here. So here we have MS, here we have SA. And if you notice, the only real difference is right here on the right, the top right corner of the structure, right? So it tells you that the same three intermolecular forces exist between both of them, okay? So this and this, they both experience the same intermolecular forces. Now, that doesn't mean the strength is the same, right? You can have the same forces, but the strength of the forces might be different. And if you notice, the melting points are drastically different, right? So in this question, you're trying to figure out why the melting point of salicylic acid is so much higher than this right here, okay? And you got to refer to the intermolecular forces. That's what you need to talk about, okay? You'll also have to refer to the structures too. So that's a little hint from me. So I'll give you guys about a minute to take a look at it, talk with the person next to you, and then we'll go over why salicylic acid has such a high melting point relative to MS. All right, so I'm gonna give you guys the answer just really quickly, just because it's a pretty simple answer. So the reason why is because of hydrogen bonding, okay? So if you take a look at methyl salicylate, right? How many spots are there for hydrogen bonding to occur? One. There's one site right here, right? But if you look at salicylic acid, how many sites are there for hydrogen bonding? Two, right? Right here and right here. And that's the reason why it has such a much higher melting point. Because two sites for hydrogen bonding, it's able to stick to other salicylic acid molecules more tightly. And so that's the reason why. It's because this guy has two sites, okay, for H bonding. And this guy only has one. Okay, that's it. And you can also say stronger intermolecular forces results in a higher melting point. That works too. Okay. But that's it. God bless you. Any questions on that? Hopefully not too bad. All right, so you guys are gonna hate the next question because it was on your test. So if you take a look at it, this is the titration chart that we had on not this past test, but the test before. I literally just copied and pasted it from here onto your test. So I'm gonna go over it but I'm gonna go through it quickly. Okay. Yes, I'm gonna go through it quickly. So I'm not gonna scroll down to part E, but part E, you're estimating the pKa. Now, if you guys don't know this, please write this down in your notes. But the pKa is going to be at halfway to the equivalence point. Okay. So pKa is at halfway to the equivalence point. So if you take a look at this chart right here, I mean, got to estimate a little, but where is the equivalence point? Or sorry, the milliliters. Yeah. It's at 10. You guys are, wait, hold on. Are we looking at the same chart? Equivalence point. Yeah, sorry. Equivalence point, yeah. Equivalence point is at 10. I was like, oh. Everyone's just gonna be my worst. My fault. I was like, dude, this is my worst pass rate ever. So yeah, the equivalence point is at 10 mils. So halfway is gonna be at 5, right? So we look at 5. You take a look at 5. Where is that around? About 3. So pKa is gonna equal 3. That's it.
What?
It's that easy. I did mention that.
You mentioned this.
You mentioned
It was
in passing. I think that's what I was supposed to do.
Yes, because I don't have time to go over. I was busy teaching us the calculations for this.
Yeah, but we didn't even calculate though.
Not on our test, yeah.
Exactly.
Okay, all right. We'll move on to the next one. We're gonna still look at this graph, so you guys can scroll down to the picture or the question below if you want. I'll zoom in a little. Okay, but if we take a look at this chart, it says the pH of the titrate, or when the pH of the titration mixture is at 4. Okay, so pH is at 4. Is there going to, oh, no, wrong way, my fault. Sorry. This is why I grade your test so hard, because you guys criticize me so much. Okay, so at pH is 4, it's asking you, are you going to have more weak acid or more conjugate base? Okay, now equivalence point is when you have no more of the weak acid, right? Okay, so equivalence point is when you have no weak acid. Okay, at pKa, halfway to equivalence point, this is when you have, okay, the concentration of the weak acid is equal to the concentration of the conjugate base. Okay, before pKa, this is when you have more weak acid, higher concentration of weak acid relative to the conjugate base.
Why should you go?
I did mention this. Oh my gosh, you guys want me to sit you down and go through your test FRQs? Well,
We're like 4 years old. Not important on the test.
I said titration is very important on the test. Okay, and so basically this is when, what is it? Weak acid is concentration is less than the conjugate base. So that's your answer. Your answer is going to be that there's more higher concentration of conjugate base. And the reason why is it's past pKa. So yeah, what's up?
For next class, I'm assuming we're not gonna get it all from FRQs today, so can I like print out the packet and then like we end up turning it in.
Yeah, of course you can do that. Absolutely. It's a lot of paper though.
Are we gonna do this strike break?
No.
Wait.
So what you guys can do is you guys can work on this as homework if you want to. We're gonna get through most of the big stuff today. I'm not gonna go through every single question. I'm gonna go through the long FRQs. I'm gonna skip some of the short FRQs and just touch on some things. Yeah, but I'm not gonna require you to do it over spring break. Yeah, I'm gonna put the answer key up as well. All right. Yeah, it's super easy to find. Hint, hint.
Yeah, who would do that?
Okay. So part G is stupid easy. All you got to do is find pKa, and you guys should probably know the formula for that, right? It's negative log of Ka. Okay, so you can just, I'm not going to even go over this. You can punch it into your calculator and you should get that. Okay. All right. Easy peasy. All right, let's move on to part H. Part H, it's telling you that you're performing a second titration. Okay. And the initial concentration of the solution is at 3.11. So this is what we have this on the test too. Okay, but you should start your curve right here. And since you start higher up on the pH scale, okay, you're going to go up at a higher place, but the equivalence point is going to be the same pH. Something like this. And then once we pass the equivalence point, we only have the base left over. And since it's the same base, it's going to stay same like that. So those are the 3 points that you need to hit. First one, the pH starts higher. Okay, second, or I guess it's 4. Second is that your curve is going to be slightly higher than this one. Third is same equivalence point, and fourth is same endpoint. Okay, those are the 4 points you have to hit. Okay. It was this simple.
It felt very hard.
Wow.
It felt-
All right. So that's gonna be point. That's the first FRQ. That's it.
Hey.
Great job, guys. You guys got 1 out of 7 so far. We're almost done.
That's just 10 points of it.
Guys, we're all gonna get a
How do you know it's 10 points?
So, yeah.
No, that's just for the that's for the entire assignment. Okay, let's move on to the second one. So second question. Okay, you're gonna like this one. We just talked about this. For part A, you have this reaction right here, and it's basically just asking you, are the hydrogen atoms oxidized or reduced in this forward reaction? And you got to justify in terms of oxidation number. Basically mention the oxidation number of hydrogen on the reactant and the product side. So I'll give you guys about 2 minutes to do this. See if you can find the oxidation numbers for hydrogen on both sides, and then see if it's oxidized or reduced. Okay, so for this, super easy. The product side is the easiest. H2 is its natural state, so the oxidation number is 0 here. Okay, and so we just need to figure out what the oxidation number for hydrogen is on the left side. Now, super easy. You should see that you have what is it? You have a polyatomic, you have me, hydroxide, and we know that oxygen is -2 in terms of oxidation numbers. So that means hydrogen has to be +1. So it goes from +1 to 0. So if it goes from +1 to 0, did it gain or lose electrons? Yeah, it gained electrons. Okay, which means that it is reduced. Yeah.
That makes sense.
Okay.
Gains electrons.
And it's reduced. Yeah,
Wow, that's-
I know. Isn't it? Okay, so that would be your justification. So it's reduced because you say hydrogen, the oxidation number goes from 1 to 0. That's all you need to write. Easy peasy. Ready to move on, guys? Okay, let's move on to part B. Okay, electron dot diagrams. Okay, I'll give you a minute to do this. Alrighty, guys. So this one should be pretty easy. Carbon has 4 valence electrons. Oxygen has 6, so you have 10 total. So 2, 4, 6, 8, 10, and everybody has 8. So you got a triple bond. Yeah. Average is always the same. Average is, I think it's like a 2 point something. High 2. High 2 is the average. Yeah. Okay, let's move on. So we got this table right here, and you have to calculate the standard enthalpy change. Okay, so if you need a hint, refer back to the chemical equation above. I'll give you guys a minute to do this. So it should be pretty easy. Okay, guys, so I have the equation up here. If you're still finishing, please feel free to finish, but at least make sure your setup is correct. So the standard enthalpy change will be sum of the products minus the reactants. So you got 198 from the 1 mole of carbon monoxide. You got 2 moles of hydrogen gas, so 131. So you add those up, minus 240, which is the reactants. And for your final answer, you should get 220 joules per Kelvin mole. Woohoo! Good job, guys.
Would you ever like a person Kelvin? No.
I think it was a last name.
Really? Oh, okay. I know someone named
Kelvin,
Kelvin.
not Calvin.
Kelvin.
Yeah, Calvin.
Kelvin.
Kelvin.
Yeah.
Wow.
Or like Avogadro.
I think that's the last name too.
No, I think that's a good first name.
Yeah, you can name your kid that. Or avocado. You know they're gonna call him avocado.
Yeah. Yeah.
Yeah. I don't know.
Chandelier.
Chandelier. Le chandelier. Le chandelier. Come here, Le chandelier. All right, let's move on. So that's part 1 of that. So let's go to part 2. Calculate delta G. And we're gonna assume that delta H and S are independent of temperature. We're not even gonna go over this. You guys are good at this already. Let me just go through it real quick. So delta G is delta H minus T delta S. Okay, you can get the delta S from, we just found it in the previous problem. Temperature is 375. Okay, and then for the enthalpy, you can get it from the equation above. And so for your final answer for this one, you should get 7.5. Okay, so if you want to jot that down, that's gonna be your answer. So if you want to try it out on your own, it'll be 7.5. Yeah.
No, it's not like if you name your kid the chandelier and they went to school, then their principal would be the chandelier's principal.
Damn. Damn, that's genius. That is pretty hard, dude. Damn. You are actually a genius. Okay, that's a good case to name my kid Le Chandelier. LC. Okay. LC. Let's move on to the last one. Or not the last one, sorry. I'm out of dude. Brendan got me all flustered now with that genius thing. Okay, so we're gonna use this diagram right here. This diagram is giving us a particulate diagram. So the particles in the equilibrium mixture. Okay, you're going to use this diagram right here to figure out the partial pressure of CO at equilibrium if the total, if this whole thing right here is 12 ATM, okay? So take about 2 minutes to try that out. You might need to take a second to figure out what's going on here. Count. Okay, that's my hint, but I'll give you 2 minutes to do that. All right, so for this one, my hint was to count. So let's count the carbon monoxide molecules. How many CO molecules are there? Yeah, 3, okay? So 3 moles of CO. How many total molecules are there? 10, okay? Okay, so that means that 30% or 0.3, okay, is going to be the partial pressure contributed by CO. So super easy, you just do 0.3 times 12 ATM, and that's going to give you your partial pressure for CO. Should be 3.6 ATM. That's it. So AP test really likes these picture stuff, so just make sure you get comfortable counting. Usually that's what you need to do with these particular problems. Yeah. 1, 2, 10. Okay, let's move on to part E. Part E is super simple. We're writing the KP. Okay, and so for this, I'm just gonna give it to you guys because this should be pretty easy. The KP is the products, the pressure of the products. So the pressure of carbon monoxide times the pressure of hydrogen gas, but since there's 2 moles and you're gonna square it, divided by the pressure of methanol. That's it.
Oh, it's not like
It is a constant, but it's going to be determined by the pressure. Oh yeah, I mean, you don't have to. The brackets represent concentration, so that's why we do it. But I mean, if you did brackets, that's not incorrect either. That is a mathematical way.
Are they gonna like points like particular about stuff like brackets?
No. Well, not for this one. This one you can do brackets or parentheses, but it's because brackets represent concentration.
Yeah.
When we're talking about aqueous solutions, you're going to want to do brackets.
Oh, but this is pressure.
Yes. Yeah. But you can still use bracket because mathematically you can still use brackets as parentheses. Okay. Easy peasy, right, guys? Dude, AP test is no sweat.
Okay. But we just have to write the expression.
Yeah, that's what it's asking for. So in part F, you're going to have to calculate it. So if you go to part F, it gives you the actual partial pressures, but you just plug these guys into the expression you just wrote. I'm not even going to go over this. I'll just give you the answer. It's 110. Okay, but the way that you find it is you just plug them in.
Or did they want to see the pressures that they found out?
All right, well, speaking of my son, LC, and his school principal.
LCO.
Yeah, LCO, Laco. Okay. We're gonna talk about Le Chandelier's principle now, okay? All right, so are you guys okay? They're dead. Okay, so it says that the volume of the container is doubled with no change in pressure and equilibrium reestablishes. Okay, will the number of moles of methanol increase, decrease, or remain the same? And you want to justify by comparing the value of Q, okay, with the value of the equilibrium constant. So you're going to have to refer back to the chemical equation. Let me write it for you guys just so you have it handy. Okay, but you got methanol, okay, in equilibrium with carbon monoxide and H2. You're going to need this equation, but basically if the volume of the container is doubled really quickly, it's going to shift equilibrium, right? And then Le Chandelier's principle is going to kick in to shift it back. Okay, so I want you guys to write down, what do you think is going to happen to the moles of methanol in particular? And you got to refer to Q and the equilibrium constant KP. So take about 2 minutes to try that, and then we'll go over it together. All right, so let's just start by talking about the increase, decrease, or remains the same. So if volume increases really quickly, what's going to happen to the moles of methanol? Yes, it's going to decrease. Okay. Now, the reason why it's going to decrease is because if you look at the left side versus the right side, you got more moles of gas on the right side, right? So if the volume increases, that means the pressure is going to decrease, right? And so it wants to get back to equilibrium pressure. And so the equilibrium, the chandelier is going to kick in and you're going to shift to the right. So that could be one way to explain it. You can say that it's going to decrease. And the reasoning why is because as volume increases, pressure decreases. Okay, and then so your value of Q is going to also decrease. Okay, and so in order to stabilize Q, what's going to happen is equilibrium shifts right. Okay. So that Q approaches KP, something like that. You could do this mathematically too, because the pressure Q is going to be the pressure of CO, but since the volume doubled, right, the pressure is going to decrease in half for everything. Okay, so you don't have to do it like this. I would never do it like this just because it's a waste of time. Okay, but the pressure of everybody is going to decrease in half. And so if you solve this problem, QP is actually going to be KP divided by 4. And so if your KP was 110, your KP is going to be 27.5. And so since it's 27.5, you're going to shift towards the products in order to bring equilibrium back. So that's another way you can explain it. Either way works. I think most of you guys will probably use this explanation. I did too. Yes.
Like
this right here?
Talk about it. Because it says to like leave the value.
Yeah, relative value is fine. You can say that Q is less than KP. Yeah, that works. Okay. All right, that's the second one, guys. Woo, good job, guys.
Yes.
Yes, you guys are killing the AP test. 5 right now for everybody. All right, let's take a quick break and then we'll come back and go on to the next one. Okay, guys, so number 3. You guys can try A and B on your own. I'll give you guys about 3 or 4 minutes to do that. They're both pretty easy. Yeah, so take about 3 minutes to do A and B. We'll go over it and then we'll move on. Okay, so for this one right here, you just need the periodic table and you just need to count till aluminum. So if we pull up the periodic table, aluminum is right over here. And so the ground state, there's 2 ways you can do it. You can do the regular or the noble gas. I'll do the regular first. It'll be 1s2 for these guys. Okay, you got 2s2 for these guys. Got 2p6 for these guys. You got 3s2 for these 2. And then aluminum will end at 3p1. Oop, not plus 1. But if you want to shorten it, you can replace this with the noble gas that it goes up to. So neon. So Ne. 3s2, 3p1. Either of these works. Okay. That's it. Hopefully all the questions are like that for you guys. And it'll be nice. Okay. Nice. All right. Okay. So for this next one, should be pretty easy. Now, if you take a look at regular aluminum, you'll see that the highest energy state is going to be N equals 3, so the third shell. Okay, but if you take a look at aluminum, it's ion, right? Al3 plus. What's the highest energy state for that one? 2. Yeah, it only has 2. Okay. And so you just need to explain, hey, the second energy level is closer to the nucleus than the third, so it's going to have a smaller radius. That's it, something like that. Okay. You can say shell. Yeah, you can say aluminum has electrons in the third shell. Aluminum's ion only has them in the second shell, up to the second shell. So that's it. Yeah.
I said that like after the third station.
Yeah, that works. Yeah. I would specify though that since it empties, aluminum's ion has 2 shells. And so yeah, you might want to specify that just to talk about the occupied one. But yeah, that should be fine. Yes. Yeah. Well, on the answer key, it only talks about the electron shells, but for me personally, I would take that because I do think that's correct. But Yeah, on the answer kit only says that, so I can't give you yes or no answer. Yeah. Depends on, yeah, how strict they've integrated. Good question, Joe. All right, let's move on to the next one. So the next one is making solutions. We briefly talked about this. I'm just gonna give you guys the steps, just to get through it quickly. But whenever you're making a solution, the key thing or the first thing you want to do is it tells you right here, you want to weigh out the solid on a scale or balance. Okay. The next thing that you're gonna want to do is you're gonna partially fill your volumetric flask with distilled water. Then you're going to add your AgNO3 to the volumetric flask. You're gonna swirl and fill to the calibration line. And then last step, we're just gonna mix. That's it. So we talked about this before. Make sure you always add the solid before you fill to the calibration line, because if you add it after, then the volume's going to increase. And so you won't have an accurate volume for your solution. Okay. Something like that. If you want to split up the steps, combine some of the steps, that's totally fine. But you do need to hit these. These are the main points to hit. Alrighty, any questions? I'll leave that up there for a little bit. And just a reminder again, I am recording this one and it hasn't died yet, so it should all be posted. Okay, let's move on to part D. Part D. Okay, so it's another diagram. This one I'm gonna go through it with you guys just step by step, just for the sake of time. Okay, but it's super simple. So you have this equation right here. And then you have the system. So this is the reactant side, and then it's telling you you have to finish up the product side. Okay. So there's three things that you guys need to keep in mind. The first one is conservation of matter. Is conservation of matter. Basically, you need the same number of aluminum and silver on both sides. Okay. So let's start by counting the aluminums. How many aluminums are there on the left side? 4. Okay. And how many silvers are there on the left side? Yeah, 8. Okay. Okay. So on the right side, they start you off with 2 aluminums. Okay. So 2 aluminums are your solid. So how many aluminums will you have aqueous? 2. Okay. So we'll start with that. All right, now on the product side, it gives you the ratio between the aluminum ions and the silver. The ratio is 1 to 3, right? So let me jot that down somewhere. Okay, so it's 1 aluminum ion for every 3 solid silvers. Okay, so if you have 3 aluminum ions, how many solid silver atoms do you need? 6. So we're gonna do 6 solid silvers.
They connected.
Yeah, you just connect the solids together. Yeah, if you separate them, they should be fine, but you want to keep them together just because solids stick together, right? If you keep them separate, they might see it as aqueous, so do it like that. Okay. All right, and then we just need to finish up drawing all the silver. So if we 6 of them solidified or precipitated, how many aqueous silvers do we have? 2. That's it. Easy peasy.
We can do this.
I believe in you guys. I'm expecting all 5s.
Oh, yeah.
Yeah, all 5s. 1 5? No, I'm expecting at least 15. Last year. Not all my years, no. Yeah. But last year was the year everyone had Chem during COVID year, and they didn't do anything. Everyone just cheated during COVID year. Everyone except Claudia cheated COVID year. Okay. Any questions about this? You guys good? Yeah, I'll leave this up here for another minute though. Okay, so for part E, we need to use the half reactions right here to calculate the value of E for the reaction. Now we know that we need we want the most positive value possible. And so we're gonna have to flip one of these, right? Which one should we flip? The second one, yeah, the one with the aluminum ion. Okay, so we flip that one. And so we get solid aluminum. It's going to become aluminum ion. And it's going to release 3 electrons. Okay. Now, if you take a look at the other reaction, do we need to flip that one? Nah, it already has electrons on the reactant side. Okay. And so we can just leave it the same. Now, technically, we do need to balance it, so we can put 3s in the front. But does that change the E value? No, it does not. Okay, so it's going to stay 0.8 volts. Not 0, 1.66 volts. And so you just add them together, and you should get a total of 2.46. Okay, so pretty easy. Yeah, the key thing you had to identify there is that you want the most positive value possible. So that's why you flip the the half reaction with aluminum. Yeah.
That's it. That's like, yeah, every time we're going to bake, it's less, nothing was positive. In this case, what we did was less positive. They saw it at the start, but we have it. So
no, it'll usually be something like this. Yeah, you'll basically you just need to flip one of them, you know, or maybe flip none of them just to make sure it's most positive value possible. Yeah, you just need to make sure that the electrons obviously cancel each other, and then based on that. Alrighty, let's move on to the next one. So based on the value of E with the standard free energy change of the reaction under standard conditions, delta G be positive, negative, or 0. Okay, so I'll just give you guys the answer for this one. If the E value is most positive, that means the reaction is going to proceed on its own, right? What do we call that type of reaction? Yes, just like you. Okay, yeah, spontaneous. So if it is spontaneous, what's the value of delta G? Yes, it's negative. So delta G is negative because it is spontaneous, because it is the most positive E value. That's your answer. Okay. Another way that you guys can actually talk about this is you can use the equation. Delta G is negative F this. You plug in a positive number right here. Okay, right? It's negative, and then you got 3 electrons. You got Faraday's constant. We have a positive number, 2.46. This is obviously going to be a negative number. So that's another way you can prove it. But either way works. Okay. Most of you guys would probably go with something like this. All right. And I think that's it. Oh, there is a G. Sorry. My fault. Okay, but everything good up to left? Okay, let's go to G. So this will be the last one that we go over today. Once the reaction stops progressing, would the change in free energy be positive, negative, or 0? So if the reaction stops, what do you guys think? 0. There you go. Okay, so delta G will be 0 because there's 2 ways that you can think about it. The first way is that reaction stops. Okay, if the reaction stops, what's the E for the cell? What value does it equal? 0. Yeah, there's no cell potential, right? And so not going to work. Second way you could think about that is that if the reaction stops, okay, that means that the system is at equilibrium. Okay, and we know that at equilibrium, delta G is equal to 0. So either one of those methods work.